this. Okay, so today we're going to talk about mathematical theory of probability. And we start with set theory, and we'll talk a little bit about, well, I'm not going to talk about measure theory, which would be needed. That's more high level abstract mathematics here. We're just gonna take a bit more abstract idea here and start with certain axioms. And now we start with some set of points, and think of this omega as the set of sample points. These are the possible outcomes of your result, you know, of your random variable. And this sigma algebra is like a collection of subsets. And why do we need this? Well, for finite and discrete systems, or finite and discrete random phenomena, we wouldn't need this kind of complicated thing, but we need it for continuous things, continuous variables. And we need it so that we can appreciate the concept of event, which is like a range of possible things happening. And the sigma algebra is a structure that captures the idea of all these possible events. So this omega itself is the set of all sample points, and this F, you can think of it as all possible events. And it has this property that this omega is an event and this empty set is an event. And then if we have these set theoretical notations that the union of events is an event and the intersection of events is an event, and the complement of an event is also an event, right? Now, as a warm-up, think about this. Think about two possible sample sets, you know, sample spaces. Two possible situations for this omega. One should be continuous and one should be discrete. And discuss this possible collection F. It says here that F can be taken as the set of all subsets, but it doesn't need to be. So come up with an example. I mean, if just as an example of a discrete situation, just a couple of elements there. A very simple case. Discuss it and explain how these axioms are portrayed there. This is a hard task, but I'm suspecting many of you have some background in set theory. So let's just use about five or 6 minutes here, and within your group, and come up with an example, either a discrete. I said first both a discrete and a continuous, but let's just say either a discrete or a continuous situation, and explain what is this collection of subsets that you are using, which are the possible events, and then explain what your how each of these axioms is exhibited, and give these events names. Give these events names, and verify that they behave like this. So come up with maybe, well, 2 or 3 or 4 or 5 or whatever it is of events, and then make sure that these axioms are satisfied. All right. So think of an example, and I'll give you 9 minutes to do this. Discuss this with the group, right? All right, so this is the basic of it. So basically what we want to do is we want to know the probability of something. So we want to assign probabilities to these elements of the sigma algebra. We want to be able to assign probabilities to events. So not necessarily points, particular outcomes, because the particular outcomes, that's not necessarily something we can even observe. We may have a theory of probability, you know, a probability theory of something that where individual points cannot even be necessarily detected. Instead, we see some range or some other kind of blurry object, which we then call events. And then these events are the things we ascribe probability to. But when we have a discrete model, then we can usually what we have is single points in our system have observable probabilities. But even so, we think of the probability as being ascribed to the set of one object and not the object itself. So let's carry on here. So let's say that we have this sigma algebra, which is then, you know, these events. Oh, yes. There's a, by the way, in the chat, there is a link now to the group that you can join and share your, you know, support for the group for students, right? So it was posted just now in the chat. So use that. So we define a probability measure on this sample space as a measure that ascribes to each of these events a probability. We call this probability. And it has these following properties. All events must have a probability that is between 0 and 1. These are the so-called Kolmogorov axioms. So a famous Russian mathematician, his last name was Kolmogorov, but I don't remember his first name now, but he was a very important pioneer in many fields of mathematics, probability theory being one of his foremost ones, but he also dabbled in information theory and so forth. So you'll encounter this name Kolmogorov in many situations.
Andrei Kolmogorov.
Andrei. Okay. Thank you. Thank you for, I've studied and taught theoretical computer science, and then there is this thing called Kolmogorov complexity, and he has other theories that he has made progress in and is very important character in the 20th century mathematics literature. Okay, carry on. So if we have a collection of events, it's possibly that it's infinite, and this sequence of events is disjoint, meaning that they cannot happen together. So let's say that, again, let's think of this as a finite example. So if we have events, the die roll is 1, the die roll is 2, the die roll is 3. These are disjoint. They cannot happen. Only one of them can happen. The probability of one of these happen, the probability that 1, 2, or 3 happens, or, you know, the union, the event, the outcome comes from the set of 1, 2, and 3, is simply the sum of the probabilities of these 3. And this extends to infinity, so that all of, if this is a disjoint events, then their probabilities are added together. And the probability of something happening is 1, and the probability that nothing happens is 0. And no other constraints here. I mean, if these are satisfied, then we can say that this P is a probability measure. So in order to come up with a model of randomness or a model of probability for some phenomenon, we need basically 3 things. First, we need the sample space. We need to know what are the possible outcomes of our random experiment. That would be the omega here. We need the concept of events. So we need to be able to know which are the events that we ascribe a probability to. What are the possible outcomes that we can actually observe? In the discrete case, we can usually observe in the discrete case, we can observe single points of this set. But let's say that we are measuring people's height, for instance. We cannot observe the actual height. Even so, the actual height might be completely ill-defined or unobservable, in the sense that a person's height cannot be determined to arbitrary degree of accuracy. If we have measuring equipment, we can, let's say we can measure a person's height only in as much that it's a range of possible heights, like within 1 centimeter. We can say that someone is between 185 and 186 centimeters. And then we ascribe to them, let's say, the height 185 and so forth. So in essence, our events in this case, the height itself is a real number, but the event of measurement, the outcome of the measurement is always just, a range between, n and n plus 1 centimeters. That's an example of a situation where the omega set of possible the omega of sample space is a set of, let's say, positive real numbers. And the event itself, however, is simply a range of real numbers. Always it's between two integer real numbers, the actual height. And then the third thing that we need is a measure of probability. So we must be able to ascribe a probability measure to each of the events. And the probability measure has to satisfy the idea that it's always between 0 and 1. The probability of measure of the whole sample space, so that you get some result, that's probability 1. Probability of the empty set, nothing happening, is 0. So something always happens when you measure them. And if you take events that cannot happen together, then their probabilities can be added. And this is not a very, it doesn't have a lot of these assumptions to it, but it turns out to be a very powerful tool. It should be noted that if we use something like a set of real numbers or so, then the sigma algebra in question cannot be the set of all possible subsets, because that's impossible. I mean, to prove this would require us to go into measure theory, and I'm not going to do that now, but take my word for it. Need sets like Borel sets or something like this. As long as it's a sigma algebra, it's fine. Intuitively speaking, the sets need to be some kind of regular sets, normal sets. And if you are really interested in the higher mathematics of this, then take the measure and integration theory course. So it has a lot of this fascinating stuff on sigma algebras and Borel sets, but that's not an issue today. So let's say that we have a sample space and we have a probability measure. Implicitly, we assume that there is a sigma algebra in play. So the theorem says that if we have a collection of disjoint sets, then the probability of one of these happening is the probability is the sum of probabilities of each of them happening separately. These are disjoint. Well, this comes straight forward from axiom number 2. We extend this to infinity by taking empty set and so forth. So that we take the n first ones are some non-empty sets, and everything after that is an empty set, and we get directly from the axioms. And an important corollary, and usually the only place where we use this, not always, but the most often used place, is that if we have two events then that are disjoint, then their probabilities can be added. Now, let's give an example. The deck of cards. Remember, we talked about the deck of cards. Sadly, I didn't bring a deck of cards here. I should have really. So you pick a card and you know that it has some suit. It's hearts, diamonds, clubs, or spades. And the probability of getting a spades is 1 in 4. The probability of getting a hearts is 1 in 4. So the probability of getting a hearts or a spades is 50-50. So that's 1 over 4 plus 1 over 4. However, if I were to say, you know, let's say that the probability of getting a card that has a number higher than 11, and let's say aces are ones. So there are 3 out of 13 cards that have the number 11, 12, or 13. So that would be the jack, the queen, or the king. That's 3 over 13 for each of the suits. And I say that it's either over 10 or it's a spades. Then I cannot add these two because some of those over 10 are spades. So they're not disjoint. So I can't do that. The same with the die roll. We had the die roll. If I say that the number is small, if it's 1 or 2, and it's big, if it's 5 or 6. So if I say that I roll the die and I get a small number or a big number, then that's 4 over 6. So that's 2 over 3. Then we can add. But if I have a big number, which is 5 or 6, and I have even numbers, there are half, 3 over 6 are even numbers, and 2 over 6 are big numbers. But I can't add these two probabilities if I say it's either big or even, because there is an even big number, so they're not disjoint. Another theorem that says that the probability of an event happening is always 1 minus the probability of it not happening. And this follows directly from the axioms. So, you know, obviously A intersection with its complement, so is empty. So A and its complement, A and not A cannot happen together, obviously. Their union, obviously, again, is the whole sample space, because A either happens or doesn't. But the probability of this is 1. The probability of something happening is 1. And then these being disjoint means that the probability 1 is PA plus P the complement of A. P of A plus P the complement of A. And you know, that just very simple algebra, you know, you get that probability of A happening is 1 minus the probability of A's complement happening. These are very basic stuff, and I assume most of you guys know this, but I wanted to give this so that you can see that these are direct consequences of the Kolmogorov axioms. And here, because they are direct consequences of the Kolmogorov axioms, these apply to all the models that satisfy the Kolmogorov axioms. It doesn't have, you only need the very simple basics of it to prove these things. If we have arbitrary events A and B, then now they may be disjoint or maybe not, then we can say that the probability of A or B happening, so the probability of A union B happening, can be obtained by adding the probability of A with the probability of B and then subtracting the probability of A and B happening. I'll give the example. Remember the example, we had the die roll. The big numbers 5 and 6, even numbers 2, 4, and 6. What is the probability that it's big or even? Well, the probability of big is 1 in 3, or, you know, let's say 2 over 6. The probability of even is 3 in 6. So that comes to 5 in 6, 5 over 6. But there is one event, namely 6, that is both big and even. So we subtract 1 over 6. So we get 4 over 6. The probability of even or big is 4 over 6. And you can verify that's 2, 4, 5, 6. That's 4 within the 6 different possibilities. 4 over 6. This follows directly from the set theory, and we can express A, any event or any set, as a disjoint union of those members of A that belong to B. I'll do the annotation. So let me know. Can you see my annotation here?
Yes.
Yes.
Good, good.
Can I, before you continue, just can I ask a quick question?
Sure.
On the slide above,
Yeah.
there's this 0 with the crossed 0. Maybe one more. Here, yeah. So does this mean no event, or what is?
That means empty set. That's empty set. It means that A is an event where there is no element. Remember that an event is a set of elements, it's possible outcomes. So if an event is empty, it means that there is no possible outcome here. So you can think of it as an impossible event.
Okay, thanks.
Yeah, that's empty set. That notational thing that's an empty set, right? So, I may not have a, let's see here. Here it says empty set is also included here. Empty set means simply the set that has nothing in it. You know, basic set theory. Yeah, okay. So basic set theory, we can know, we'll rehearse set theory a little bit. So if you don't remember exactly how this is. So here we have the set A. So we can divide the set A into two parts. Those elements of A that are also in B, and those elements that are not in B, right? So if you have a set, I can draw a Venn diagram, fairly simple. Just get a pen and paper here. So here's my set A, right? Here's my set A. That's my set. I mean, everything inside that circle. And here is my set B, right? Here's my set B, obvious. So this divides A into two parts. A intersection B and A intersection the complement of B, right? So those elements of A that are in B and those elements that are not in B. So this divides A into two different parts, which are disjoint, obviously. An element of A that is either in B or not in B. So these are the ones that are in B and these are not in B. So we can add those two together. Here we can then easily just rearrange the terms to get A union B. Well, in A union B, I mean, not rearrange it, but let's apply the same to A union B. So A union B divides into two parts. Similarly, the elements that are in B and the elements of A that are not in B, right? This A union B contains both these circles. So these are the elements that are in B, and that's the elements that are not in B. So we can express A union B similarly. And now we can then just replace, we can replace this here by probability of A minus the probability of A intersection B, and we get this formula here simply by rearranging the terms here. This B. So this is simple set theory and simple algebraic manipulation of these additions. So there's nothing weird here, but the interpretation should be relatively clear. Think about this. Now, the probability of something here happening is the probability of all the stuff that is in here happening plus all the stuff that is happening here. But now look, this region here, A intersection B, this shaded region, that just got counted twice. So we need to subtract this from adding B and A. All right. Here's an example of the deck of standard playing cards. What is the probability of being an ace or a spade? Well, there are 4 aces and 13 spades, but one of the aces is an ace of spades. So we get 4 over 13 as our result, 16 over 52. Right. Now, I'm going to clear those drawings here. So let's continue. But before we do, I'll have you do a little bit of group work again, because this is very important. All right. So like I said, or like we discussed, if you have a hearts or even, that's 31/52. All right. So let's move on. So we can express unions and intersections and complements and so forth with set theoretical notation. But there is another thing that we want to discuss. Let's say that we have two events, A and B. And we know that one, in this case, let's say B has happened. We've carried out an experiment. We've received partial information about the experiment. We see that B happens. And we don't know whether A happened. Let's say that we only get partial information, like we don't get the actual point that is there. We don't get exactly what happened, but we know that the event B was what happened. So let's say we roll the dice and we know that we got an even number. We know that we got an even number, but we just don't know if it's, or let's say we got a big number. Or even number or big number, doesn't really matter. We want to know whether this affects our probability of or whether we should revise our idea of did A happen or not, and what is the probability that A also happened. So this is a very important, a highly important application of probability theory in which we have a model of uncertainty. That's the probabilities. Then when we observe an event, then we need to be able to verify, or not verify, but we need to be able to calculate, would this be also the case that A happened? Does it increase or decrease our probability of A also happening? So because A is an event and A intersection B is an event. So let me just show you, let me draw a picture of this, try to give you an idea. So here's the set of all possible events. So before we observe anything, we know only that when we conduct an experiment, something from this box happens. We don't know what. And let's say that here is a B. And here is A. Here is A. We observe that B happened, so we know that we are somewhere in this circle. Now the question is, what is the probability that A also happened? Then it's in this, my example here, if B happened, the probability that A also happened happens to be actually quite a big proportion of this. Let's say that it's roughly the area here. So that knowing that B happened, quite a few of those B occurrences are in fact also occurrences of A. There are some A's that happen outside B, but if we know that B happened, it is actually more than 50-50 chance that A also happened in this picture, if the area is roughly that. So the event that happened, if A also happened, then we know that B happened. If A also happened, then we know that A intersection B happened, right? So we know that B happened, it's this circle here. If A also happened, then we are in this this region here. So the conditional probability of A happening under the assumption that B also happened is what we're looking for. It's denoted like this: the probability of A on condition of B. So let me revise my example of big and small numbers. I said, let's say we have rolled the die, and for now, let's assume that the big numbers are the numbers 4, 5, and 6. Okay? And then we have even numbers and we have odd numbers. Let's say we know that we got a big number. We don't know which one of the big numbers is, but it is a big number. So we know it's 4, 5, or 6. So knowing that it's one of these three, then it's an even number. Well, which of these three are even numbers? 4 and 6. So the probability of it being even is now 2 over 3. It's not 1 over 2, it's 2 over 3. So knowing that it's a big number, we now know that it is more likely that we have an even number. That's the idea of conditional probability here. So if we have the definitions of A and B, how do we calculate this? Well, I'll explain shortly why this is so. If A and B are events, we have to assume that the probability of B is greater than 0. So if it's an empty set, then this doesn't work. Well, it doesn't work and B cannot happen, so we don't even define this in any way. The conditional probability of A under B is simply defined as the probability of both happening divided by the probability of B happening. Now, to make sure that this is a number between 0 and 1, it's obvious that probability of A intersection B has to be smaller than or equal to the probability of B. So this quotient is going to be a number smaller than 1, and because both are positive, it's greater than or equal to 0. So both are non-negative, sorry. So this is greater than or equal to 0 and smaller than or equal to 1. So this is a probability of something. Why is it the probability, conditional probability of A happening knowing that B happened? Well, if you think about it, if you think about this example and think in terms of surface area as being indicative of the probability, then we now know the actual probability of the A happening here in general is the proportion of this A surface area of this whole box. And in this case, it's relatively small, less than a quarter. But now that knowing that B happened, it's the proportionate area of this part that is also in A of the circle that is B, and that's now more than 1/2. It actually looks like it's about 2/3 or even a little bit more. So you can think of this as knowing that B happened, we can think of this that our range of possibilities is now restricted to those that are members of B. So our kind of smaller sample space, we've ruled out the possibility of B not happening. This is a very important concept, it's conditional probability. And this definition, we can also express it as what is called the multiplication rule of conditional probability. So the probability of A and B happening is the probability of B happening times the probability of A happening under the assumption that B also happened. It's just a rewrite of this formula, this definition. But if we know these conditional probabilities, then we can express it like this. So here's an example of a study. So a study shows, and let's say that this study shows that we've studied this phenomenon of traffic accidents, and let's assume that it's, before we go in depth into this material, into these actual numbers. So let's assume the traffic accidents are a random phenomenon. And there are causes to traffic accidents which are either technical failures, meaning, a tire gets blown, brakes don't work, something like this. And poor driving skills obviously can be a causative factor as well, or it can be a case of both. So maybe your tire breaks, but if you were a good driver, you would be able to steer clear of the person that you are going to hit. But because you're a bad driver, then your tire blowing up causes you to hit someone else. So it's a mixture of both. So and this, when I say caused by, we can say associated with, for example. So let's say that we observe an accident and we want to determine whether there was actually poor driving skills involved. How likely is it? So 5% are caused by both. 55% of all traffic accidents are caused by poor driving skills. So let's call A the idea that accident caused by poor driving skills, B an accident caused by technical failure. We observe that there is a technical failure in this case. So what's the probability that the driver had poor driving skills? Well, it's the probability, conditional probability of poor driving skills under the condition of technical failure. Now, again, let's say that we know that both are in play in 5% of the cases, so that the probability of both being the case here is 0.05. The probability of B, the probability of technical failure is 0.12, so that's 12%. And the quotient is 0.42. So whenever there's a breakdown of something, there's still 42% of those cases are still would have been avoided if the driver were done a better job. So this is how you use conditional probabilities. Let's give another example. Let's say we have a group of 30 people. 20 of those 30 people have an MSc degree. So we take 3 people at random. What is the probability that each and every one of them has an MSc? So out comes first the guy. So this seems like, combinatorics, but we can actually use the conditional probability here. I'm just going to show you something here. So first comes out the person. What is the probability that they have an MSc? Well, that's 20 out of 30. What is the probability that the second one has an MSc? And so forth. So we can express this using conditional probabilities. This is not usually the way it's used, but I wanted to show that you can actually use the conditional probabilities to deduce things about combinatorics. So the probability of all of them having MSCs is, you can use the multiplication rule. The third one still has an MSc. Here's the conditional probability. The third one that comes out has the first two have MSc degrees times the probability that the third one still has an MSc, even though the first 2 ones already had an MSc, which you can then express that the first one had an MSc times the second one had and the first one had times the probability that the third one had and both of them had, both the first and the second one had. So what are these? Well, this conditional probability is simply the probability that involves the computation that how many are there left. In the first case, when the first one comes out, there's 20 of 30, right? This is 20 out of 30. But the second one, now the conditional probability that the second one comes out after the first one had an MSc is 19 out of 29, because there's now 19 MSCs left out of 29 persons. And the probability that the third one is out has an MSc, given that the first 2 had an MSc, that's 18 MSCs left in a group of 28 people. So that's about 28% the whole probability, multiplying these together. Okay, usually you wouldn't use conditional probabilities in a question like this. You would just directly jump into the idea that, okay, the first one, that's 20 over 30, then the next one, that's 19 over 29, and the third one, it's 18 over 28. And that's perfectly fine. You can do it like this, but be wary or be understanding or aware that actually what you were doing there was conditional probabilities. That's something that you know, when you're doing combinatorial problems, like, you know, I already picked that one card, that one was there, and there's something left. Okay, and what is the probability? So you're using actually conditional probabilities there. Because everyone knows this card. I don't know if everyone knows, but I mean, I hope that you have a high school equivalent of combinatorics, like, you know, you pick one, and, you know, how many are left, what is the probability then, and then you pick another one, how many are left, what is the probability left, and so forth. So this can be framed in terms of conditional probabilities, and I really do urge you guys to do that, because it helps you in thinking. All right. Here we should have a little bit of an exercise. So I'll give you an exercise. I'll have a stop this recording for a while. All right. So now that we know what the conditional probabilities can be calculated like, you know, so we know the two events, we can calculate their joint probability and then divide the, let's say, the unknown. We know that one of them happened. But again, let me just refer to this picture. So we know that one of them happened. Let's say we know that this B happened, and we want to know what is the probability that A also happened. And then it's the proportion of this area to the whole area of B, you know, proportionate probability of both happening to just B happening. It's always a subset here. Now, Bayes' formula can be expressed relatively straightforwardly by simple manipulation of the formula, but I'd like to just define it in a slightly different way. So let's start with this idea that the sample space is partitioned into events. So I'm going to just draw you a picture. This is partitioned into events, let's say like this. And partition means that each of these samples belongs to one of these sets, B1, B2. I'm going to draw here. So in this case, I have 6. So there are 6 partitions here, right? And now we have a event A happening, and let's say that it's the event A looks something. The event A is this circle here, right? So we know that A happens, and the probability of A happening is the sum of these small parts of different B's. You can add the probability of, get the probability of A by adding these small parts here. You don't necessarily know them, but let's assume that we know these, but we don't know exactly the A, and we don't know exactly, we know exactly the B's, we know these parts in this A, but we want to determine the probability of A, given that we observe one of the B's, or we want to determine the probability of each individual B, given that we observe that A happened. So we can express this in terms of conditional probabilities. I mean, obviously the probability of A is the sum of these regions that come from different B's, right? Assuming that each of these B's is non-zero. We can get the whole A's probability by using the multiplication rule, by applying each of these are disjoint, right? These are disjoint, obviously, because B's are disjoint. Then the probability of A is the sum of all these intersections. But then we can use, in each of these intersections, we can use the multiplication rule to get it in terms of conditional probability. So the probability of A is A happening, right? Can be said that, you know, it's the sum of the probabilities of each B happening, and then that times the probability of A happening if that B happened. So let me give a very straightforward answer. Let's say we have 3 people and someone was murdered. We know that one of the 3 people is definitely the murderer. So the probability of the murder happening is the sum of probability that actually person 1 murdered them, you know, murder happening, the probability that person 1 is the murderer and they murder it, plus the second person and they murdered it, plus the probability of the third person and they murdered it. And the probability of someone getting murdered is that the probability of the murderer is the first one and murder happening if it's the first one. So let's say that this is like, you know, what is the probability of person 1 committing, you know, having a reason, let's say having a reason to murder someone. And, you know, what is the probability of them being the murderer? We can solve this. We can solve this. We want to solve the probability of person, let's say 2, being the murderer, given that someone was murdered. Or let's say that it was murdered with a knife. And let's say, you know, person 1 prefers guns, person 2 prefers ropes, and person 3 prefers knives, you know, with conditional probability. They tend, these are, let's say these are serial killers that have a certain usual way of murdering people. And we wish to solve to each individual, you know, suspect, what is the probability that they were the guilty party, given that this A, which is the evidence, let's say that the killer used a knife. So we can express this probability with the Bayes formula here. I'm going to use this. So remember, let's say that this probability that knife is used is the probability of a particular individual being a killer, and the probability of that individual using a knife if they kill someone. So the probability that someone is a killer, given that they used a knife, is the probability that they actually use a knife and kill someone divided by the probability of knives being used in general. And then this, we use the product rule on that. We get this probability here of person K being the killer times the probability of them using a knife divided by the probability of a knife being used. And, oh, that annotation, just let me clear those. So we can replace this probability with this sum, and now we have a generalized version of the so-called Bayes formula. Usually this Bayes formula is given with just one possibility. So if we define that, if you look in the literature and find the Bayes formula, then usually what you express it like is that the probability of B under condition A is the probability of B times the probability of A under condition B. Divided by the probability of A. This is the usual format in which Bayes formula is given with just A and B. But here, really, I mean, this is much more intuitive to understand that we have to take here into account. We don't usually know the probability of A per se. We may probably know these MOs, you know, each suspect, probability of each suspect using a knife, probability of each suspect actually being a killer, and then we can come up with the probability of a particular subject being a killer given that knife was used. Well, that's a little bit of a how should I say, grave or morbid example. So let's use a more suitable for applied mathematicians, a suitable example for applied mathematicians. Unless you become a forensic scientist, and they actually do a lot of these bias formulas. I mean, and if you look at these TV shows, they don't mention it, but actually they use bias formula quite a bit. But let's say we have a factory that produces products, and we have testing apparatus for these products. The particular method that we use has a certain reliability. It can reject low quality products fairly easily. High quality products are not usually rejected. Well, fairly seldom rejected, and defective products are rejected with a very high probability. And maybe it's a camera that looks at certain things about an object that is coming on the conveyor belt. I don't know. So high quality products, we can sell them for very high price. The low quality products, maybe we can use them somehow or sell them or distribute them. Maybe they have some use, but we don't want to ship them out to be sold. And the defective products, they have to go to recycling. Let's say that we want to do this. And our automated testing device has a 90% rejection rate for defective products. So if there's a defective product comes through the testing, it has only a 10% chance of being pushed forward and given to someone. If it's a low quality product, it's rejected with 70% chance, but 30% of low quality stuff goes through. And there's a 0.1 probability that a high quality device is rejected. So let's say that we are looking through the rejection pile. So, let's say they are pushed aside and we look at the rejected apparatus. So we ask, what is the probability that is useless? It's completely defective. Remember, to begin with, only 1% of all products are defective. So we have the probability of B1 is 0.01. That's a defective product. Probability of B2, low quality, but maybe usable, is 0.05. The probability of having a high quality product, 94%, 0.94. The probability that an element is rejected, let's say this is A, if it's B is 0.9. If it's B1, it's 0.9. The probability of it being rejected if it's B2 is 0.7. The probability of it being rejected if it's high quality is 0.1. So we can substitute these in the bias formula. Obviously, the probability of being rejected here, probability of being a low quality is 0.01. The probability of being rejected if low quality is 0.9. And then the probability of being rejected in general is gained by adding all these conditional probabilities, like if it's defective and rejected, if it's low quality and rejected, and if it's high quality and rejected. So only 6.5% of those rejectees are are defective, we can similarly calculate what is the probability that it is high quality. It's actually pretty amazingly high, the probability that it's a high quality. It's amazingly high in this situation. Far more than the 10% that is the probability of it being rejected if it's high. So really, this is an example that you should go through. I'm not going to put you through it now. I want you guys to go through this example in your own time and calculate all the other conditional probabilities. What is the probability of it being low quality, and what is the probability of being high quality? And see that these so-called prior probabilities, these probabilities before testing, have a huge impact on how likely it is to be of this, how they appear after the testing, what kind of distribution, if you will, emerges after the testing. It's really very fascinating and important, because this is something that needs to be, I mean, in this day and age, in now, especially when there are these, virus outbreak, this pandemic of the coronavirus, there are tests that are not completely 100% reliable. They are pretty reliable, but still, masses of people are being tested. And of course, there are massive numbers of rates of infections in many countries. So the question would be that, knowing the reliability of the test, what is the probability of the false positive, that a healthy person gets a positive result? What is the probability that an infected person gets a negative result, and so forth? If you look at people who tested positive, there are bound to be several people who are healthy, and people who tested negative, there are bound to be many people who were actually had the virus. I'm not saying this is not critique of anything. It's just you have to be aware that this kind of phenomenon exists, and to be aware of those numbers, what they look like given a certain rate. So if someone tells you that this test is highly reliable, it only has a 1 in a million chance of being positive, false positive, and you get a positive, then what is the chance that a positive person has the illness? Well, if it's the coronavirus, it's fairly common. It does occur quite often. But if it's some disease that is known to affect only 1 in a million persons, then it's close to being 50-50 if you test positive, and if it's a very rare disease. So I'm just saying, this Bayes formula is a very important tool for understanding the real world. All right. I'm not going to talk about Bayesian interpretation of probability this time. We'll talk about it a little bit on next Monday. Next week, we'll move towards independence of events. We'll talk about those a little bit more next week. And we hope to get to this chapter 1, end of this chapter 1 by then. All right. That's it for the lectures this time. I'm going to stop the recording.